Okay, so we are at the IIT Kanpur are very happy hosting this workshop in honor of Dr. Srinivasan, who passed away last year in August. And LENR has been a field which started around 30 years ago. And it is a field where anybody who cares to check starts seeing that things are, what is being talked about is real, and the detractors are those people who do not bother to check. And Dr. Srinivasan has been one of the pioneers. He was there from the very beginning. And I am happy to declare this workshop open and hand over the reins to Professor Pankaj Jain to conduct the first session.
Thank you, Rajiv. So I am Pankaj Jain, so I will be actually conducting this session. So let us start. I mean, we are looking forward to, I've actually heard all the talks for today's session and looking forward to a very, interesting discussion on all the talks. So I'll request Jean-Paul Barbarian to start sharing his screen and start his talk. Okay. I request him to give, a brief presentation, and then this session, as we all know, is basically meant for discussions. But before that, we request him to briefly present his main results.
Okay, thank you very much for the invitation, and I'm very happy to talk about my work because I had very good times with Chino. We spent a lot of time together. I remember at every conference, as I am vegetarian and he was vegetarian also, he was following me so to know what to eat and what not to eat, so it was great. He was just always behind me at the dinners. He invited me when he organized ICCF 16, so I spent a lot of time there visiting different universities also with him. That was a great, great time. So I am so happy to talk about transmutation because he loved transmutation, and we talked about it many times. And this work is related to transmutation. Actually, I think you have listened to my talk already, but this is not my original work. This is just a replication of Mastro Matteo's work. I've done the same thing as he has done, and I've observed very similar effects than he has observed. So this is a very good thing because we have different. Somewhere. Can you guys turn your microphone off?
That's feedback.
Feedback, yeah, no, but what a feedback. So I've done the same thing as he has done. So it's a replication. In addition, in the meantime, it's not yet done, but we are doing, we have put a CR39 to measure neutrons. So in a few days, I hope to have the results. And that will be important to know if we produce neutrons or not during this kind of experiment. And also another point which is quite important, the laser doesn't seem to be completely important, but because Mastro Matteo has put a sample without laser, and he also observed transmutation just by hydrogen. So the laser might be amplifying the effect, but it's not necessary. So this is very, very intriguing. Why does hydrogen in palladium create nuclear reactions? Anyway, now I'm open to questions.
Okay, so I request participants to come forward with questions that they might have. They may just unmute themselves and ask questions.
I am Rajpala from IIT Kanpur. So you were mentioning that the laser does not play a role. Is there a difference in the extent of transmutation with and without laser?
Well, it seems that with laser, there's more transmutation than without laser. But actually, maybe there was some reflections on the walls of the chamber or something because both were together. In the Mastro Matteo's experiment, both samples were in the same chamber, One was under the laser beam and the other was outside of the laser beam. But you never know if there was some reflection that could have affected a little bit the surface. That I don't know. I have not done this experiment myself, so I cannot give you a conclusion. I think
And
the laser is better to have it, yeah.
And you also mentioned that it took 3 months to do the experiments, right?
Yes.
So in the sense that you had the sample with hydrogen and with the deuterium for 3 months, or?
Yes, yes.
Okay.
Actually, at the beginning, I wanted to do it only for 2 weeks, but then COVID arrived, so I couldn't do analysis, so I left it all the way during the lockdown. So it lasted 3 months. So when I repeated the experiment, I used the same 3 months period to accumulate as much as I could, you know.
Okay.
I've done the same thing with the neutron detection. I left it for 3 months also. So we'll see what happens.
All right.
In your
okay, sorry.
Okay, Paul. Raj.
Go ahead, Rajiv.
Go ahead.
Rajiv, go ahead, please.
Yeah. Professor Barbarian, in your case, the transmutations were observed only around the crater, right? Where the laser beam was falling, right?
The crater I showed in my picture was the largest one. There are smaller ones also give transmutations. I have done analysis again 3 days ago, and we have found other spots. We have also transmutation. But this one was the biggest one. It was really amazing. Right at the middle of the sample.
So the crater was where the laser light was falling, right?
I'm sorry?
No, was the crater was located at the place where the laser light was falling?
Yes, absolutely.
No, but you also said there were minor craters.
Yes, there are minor craters around it also. Yes.
Was there laser light falling on those places also?
There are also all kinds of elements also. Yes, same kind. Actually, I'm calling that a crater, but it's not really a crater because it's not really deep. It's more like a different kind of material constitution. It's not like a deep crater, like a volcano. It's not like volcano. I tried to look for molten areas, but I couldn't find any. So it's not like something happened and melted the palladium. Nothing like that. That's my point of view.
But did you see crater also when you had no laser beam? What happened in the case when you had low? Did you see hot spots in that case also?
I didn't do the experiment myself, so I don't know. Maestro Matteo found some hotspots also, but less intense. But he found also some. Yeah, it seems the laser.
Even without laser, there were some hotspots.
Yeah, there were some hotspots.
Yeah, please go ahead.
Yeah, that's correct. There is a hotspot without laser. But as I was telling you, they were in the same chamber, so maybe there was some reflection of the light there. I don't know. Could be done. It is necessary to do an experiment completely separate with only no laser at all. Maybe I will do one day. Yes.
Okay, thank you.
Welcome.
So, other questions?
Has some XRD been done to see whether there are some surface phases of palladium hydride or something like that?
No, I didn't look at that. I didn't try that. I don't know how to. Well, it's a thin film. You know, the film is only 350 nanometers thick, and probably there is palladium hydride. There is palladium hydride for sure. But when you look at I use scanning electron microscopy to look at the images and the composition by EDX. So I cannot find out if there is hydrogen or not. In the future, I hope to do SIMS analysis, so I will find more about the composition of the material, yes. But when you put palladium hydride in air, most likely hydrogen will get out of the sample because the affinity of hydrogen with oxygen is more than the affinity of hydrogen or deuterium with the palladium. So most likely it will go away.
But see, when palladium reacts with surface, palladium surface may dissociate hydrogen, right?
Yes.
So therefore, the chances of it forming hydride is, even though it may react with oxygen, but the dissociation might not occur. I mean, maybe unless it's both of them get co-adsorbed on the surface and they form H2O on the surface.
Yeah, what's happening? I've done many experiments of this time. I used the palladium foils loaded with hydrogen or deuterium, and as soon as I bring them to air, they heat up very quickly and become red hot because the reaction of hydrogen with oxygen, you know, because
Okay.
oxygen will pull out the hydrogen.
Okay.
Yes. In vacuum, under vacuum is no problem, but as soon as you
Yeah.
go in air, you have oxygen, so that's an issue.
So I have a question.
Yes.
So in your talk, you identified some possible reactions that might be occurring. They were possibly fission reactions.
Yes.
So for example, you mentioned that palladium may be going to iron and calcium.
Yes.
So do you have any idea which isotopes of these elements might be formed, or that particular information is not available?
Now, I've done some calculations using masses, you know, products before and after, and you realize that not all the isotopes of palladium and not all isotopes of calcium or nickel or iron are produced. I have a table on that. I didn't put it in the PowerPoint, but I have done that. And only very few isotopes react, actually. So that will be a good check when we do the SIMS analysis to find out if we have the same types of isotopes. But you're right, not all isotopes will work. And when you have isotope producing fission of palladium, then you have only one neutron being produced every time, not more than one, never two neutrons, only one.
Okay. So I mean, what is potentially happening? Could it be that, I mean, hydrogen is first undergoing a fusion with palladium and then it's producing fission, or do you think that is probably directly a fission of palladium? What is likely happening in this process, in this experiment? Do you sort of have some ideas on that?
It is similar to uranium and neutrons, you know. When you put a neutron in a uranium-235, you make fission. And it seems that here you put a proton and the proton react and make fission. There's only lighter elements, there's nothing heavier. In some other experiments, I've measured formation of silver, but that was electrochemical reaction experiments. Here we see only lighter elements, definitely a fission reaction. It's very similar to uranium-235 and a neutron, you know, but it is a proton. Maybe it's
Thank you.
reaction.
Why do you think there was so much of oxygen in the reaction products?
That's a good question because there's not oxygen. I mean, oxygen, palladium doesn't react with oxygen, and nitrogen is even worse, you know, because nitrogen, you cannot dissociate nitrogen molecules like that. It's hard to dissociate. It's one of the most stable molecules, nitrogen molecule. So how come there is so much oxygen and so much nitrogen, unless it is produced by one of the reactions I put in the presentation? You know, I can show you where are they? Oh man, I have to go to the. I'm sorry, I'm trying to put you to show you the different. I've lost my presentation. Where is it? At the end, I put a table of all these reactions. Here, you can see.
No, we cannot see the presentation. I mean,
presentation. Okay, I put it full scale. Now you can see it.
yeah, now
Yeah.
it is there.
Okay, now you can see that to produce oxygen, you can have palladium transform into zinc and oxygen in the second group of reactions. And if you can have also oxygen if you dissociate palladium into oxygen and phosphorus, and you can have nitrogen when you dissociate palladium into nitrogen and sulfur. That's the only way I could find oxygen and nitrogen in terms of exothermic reactions. They have to be exothermic to happen, you know, otherwise they will not produce and it will not happen. So I don't know what to tell you more about that. It's SIMS analysis will be very important to know actual isotopic distribution.
No, but was the zinc concentration and oxygen concentration in 2:1 ratio or 1:2 ratio?
Which one? Oxygen and what? And
Oxygen and zinc.
Oxygen and zinc, for instance.
They should be in the 1:2 ratio, right? Or 2:1
The
ratio.
phosphorus and so on, right?
But,
Phosphorus also.
yeah, there's
Okay.
also a reaction with phosphorus, so it's a bit complicated to do that. Yeah, I agree.
Okay.
Yeah, it's a bit difficult to do that. There's several origins to the oxygen. And same thing for nitrogen, because nitrogen is sulfur, but sulfur with zinc, so it's not that obvious.
Any thoughts on why hydrogen behaves very differently from deuterium?
That's a good question. I have no idea, because deuterium, in my case, I didn't see any hotspot. Mastro Matteo has found some of the hotspots, but very few. I couldn't find anything. Maybe there are that I didn't see, because the sample is only 1 square centimeter and the electron microscope analyzes very small areas. So maybe I missed some, but there is nothing really big happening with deuterium. I don't know. The only thing I know is that one is a fermion and the other one is a boson. Maybe there's a difference there. Could be some theoretical work needs to be done there.
So you said that in this slide, so you said that argon was impossible to detect because it was in gaseous form. So would the same thing apply for helium if it was present in the reaction?
Absolutely, yes, yes. If there is helium, you will never see it. Yeah, it will go away very quickly.
So I'm just pitching it. So maybe deuterium didn't show any reaction because there wasn't there wasn't any helium, there wasn't any hydrogen for fusion or something.
Okay, that's possible. Yeah, maybe you produce helium and then you don't see the helium. That's possible. Yes, yes.
Hello, sir.
In the case of deuteron, the palladium did not change. I mean, the concentration of palladium remained almost the same, right? It did not change too much. Did I get that correct?
I'm sorry.
Professor
Yeah,
Biberian?
can you repeat your
Because
question?
in the deuteron experiment, the concentration of palladium remained almost the same. It did not change much at all.
Yeah, that's true. But
Is that correct?
That's correct. But if the deuterium reacts by itself with another deuterium, then that's possible, yes. But,
yeah, right. Okay, of course, sure. Yes. Yeah.
Deuterium fusion.
Yeah.
Different. I have to tell you the truth. I have now put a lead sample to see if I can make gold like the alchemists did in the past.
You're not telling us, did you make the gold? No, you're not telling that.
I don't do I don't know if there's gold yet.
Okay.
So when do we expect the SIMS results to be available?
Maybe 1 month from now, maybe, yes.
Okay. Francisco, you're trying to say something, but you're muted. Please unmute yourself. Francisco,
you want to
please
talk?
Unmute yourself. Yeah.
Unmute.
He's unmuted now, but his voice.
There's a lot of static.
Francisco, it's not coming somehow.
Francisco, unmute.
So meanwhile, probably I can. I wanted to make a comment, Professor Biberian, sir. I saw the PPT, and then the primary tool that has been used to collect the result is the EDX.
Yes.
So a few minutes back, Professor Rajiv was asking a question about the presence of oxygen on the samples. I would like to mention one thing. Using this EDX machine, we actually can also characterize our samples, the samples that we are analyzing, on the basis of oxides of various elements. So basically, EDS empowers us to do that. So in order to, however, in case of your results, we find that these oxygen, I mean the high concentration of oxygen, are only found within the crater. I mean, within the region where the reaction happened, or we call it the hotspot.
Hotspot, yeah.
And the region which are beyond that ring or the boundary of the hotspot, there we find so nearly no oxygen is present there. Only, so basically 99 atomic percentage palladium is present.
Yes.
So I think we can also answer the questions why oxygens are present only at that region, that too in high concentration. Maybe we can run this EDS in that mode where it allows us to characterize that sample in. So that's a particular mode where we can actually do that. I mean, we can find which metal oxides are present there. So probably I think one should do that also. One should run the machine in that mode also. So that would give us a lot of insights for the.
Can you tell me more about this mode of the operation of the EDX?
Yeah. So, sir, we have so actually this. So what it does is basically collects this X-ray energies, characteristic X-ray energies of the elements, and
Yes.
then relative to the intensities. I mean, the intensity, the relativeness of the intensities basically tells us what the atomic ratios are. So the results that we saw in your PPT were actually the relative intensities of the different chemicals or the different elements that were observed on the particular point where the beam was, where the electron beam was put on. So what I am saying is that basically we can just, in fact, the company that you used, we also use the same company's machine. I mean, the brand is same.
Yes.
So probably you just have to ask the operator to go in that mode, and then it will collect the data in that mode. So that will give you various concentrations of metal oxides.
Okay. All right. It's a good point. Okay. Thank you.
Okay.
I will check.
We can continue this discussion later. So Francisco has written, he has a question about focusing of the laser and wavelength in comparison with Mastro Mateo experiment.
Okay.
So can you say something about that?
Yeah, Mastro Mateo defocused the beam to cover the whole sample. In my case, I left it as it is, and it was about 4 square millimeters in size, whereas it was more intense, I think, than the Mastro Mateo's beam. Yes, he was covering the whole sample, and I was not covering the whole sample. I was covering only the center of the sample. But it's hard to know exactly where it was pointed out. But the hotspot I showed is exactly at the center of the sample. And the wavelength is very similar. I don't know if the wavelength is important or not. Maybe it is, but more work needs to be done in that direction.
Okay, thank you. So I think we have finished the time for the first talk. We should now go over. So thank you, Professor Barbarian.
Thank you.
We can come back to more questions in the discussion session. So I now request Jed Rothwell to start sharing his screen and give a brief presentation.
Hello.
Jed?
Yeah, hi, can you hear me?
Yeah, we can hear you.
Well, I've already read the whole presentation. I presume people have seen it. How does this work?
Yeah.
Yeah.
We see.
Why don't you just put up the slides if you would? I guess I don't know. I can put them up on this computer. What do you want me to do?
Yeah, that would be better, I guess.
Sure.
If you can share your slides,
Sure,
that will initiate some
say a few
questions.
words. Let's just briefly review your talk, so
Yeah,
people are reminded of it.
People who didn't see it. Hold on, just a minute.
Yeah, that's right.
No, maybe we all saw too many talks in a day.
There are too many. There are far too many. PowerPoint. I wasn't ready for this. You can. Just a minute. Hold on. Memorial. From the beginning, slideshow. If I do this, it's going to start talking. I don't know how you shut this up.
But if you don't put it in full screen, I think it won't
Yeah.
start the audio.
just ordinary like this. Hold on, let me share the screen. Hold on. Sorry about this. Didn't know what you planned to do here. Where are we? Stop video, mute. I've never done one of these. Share screen. Here we go. Can you see it now? This is not.
Yeah, right. Yeah,
Okay.
You can see it now.
Yeah, this is not the display format. But see if it works. Hold on. Yeah, there we go. It's a very short presentation. I'm telling you about the results from Dr. Muto and Saito, who replicated Mizuno's experiment. Saito was Mizuno's graduate student 20 or 30 years ago, and he and Professor Muto went ahead and did an experiment very similar to Mizuno's. And then they had a couple of undergraduates who did the actual work. And those two people wrote a graduate thesis in Japanese, which I translated. Can everyone hear me? I can't hear myself or anything.
We can hear you.
Good. Okay. Okay. Well, this is Mizuno's experiment. Two reactors side by side, the control and the active one, and you insulate the box, and it's just airflow calorimetry. The air comes in here, goes out there. The temperature difference multiplied by the mass of air times the specific heat of air tells you how much heat there is. The same as water flow calorimetry, but it doesn't work anywhere near as well. And here's the best result from a couple of years ago. Here it is expressed only in temperatures. And you see the blue line, which was the excess heat, is way above the calibration at 50 watts. So this gap alone is pretty good proof that something was going on. You don't need to do any adjustments to see this. Anyway, as people probably know, we distributed meshes. We uploaded a detailed recipe, and Bavarian and others tried to replicate, but they got nowhere, unfortunately. They couldn't replicate it, which is a great disappointment for us. 3 people did replicate it. And if you get the slides, you could click on the links right here. And the one that replicated best was, as I said, Saito, Muto, Igarashi, and Nida. It wasn't really a replication so much as a collaboration, because Mizuno went over there and helped them. This is their equipment. Only one reactor I see. This is a whole lot better than the equipment Mizuno's got, because they have more money. They have an SEM machine. They have, this is a much better environment. The air temperature is stable. So here's some of their results. This is unadjusted. You know, this is the gap here is for the heat lost from the reactor chamber. I'm sorry, from the calorimeter chamber. And the excess is just a little above that. And here it is adjusted. This is corrected for heat loss. As you see, there's a heat balance here and considerable excess there. And 345 watts, 400 watts. What keeps happening, I don't understand, is that the excess heat always seems to equal the losses from the calorimeter chamber. That does not make any sense. Why should, it's just a coincidence, they say, but I don't understand why that is, and they don't have any reason. They don't know either. And here it is, corrected, it's fairly high up, but uncorrected, it's always right on top of the calibration. And here's 8 power levels. It doesn't increase. The percent of excess heat does not increase with higher temperatures, which is unlike other cold fusion reactions. Well, okay, you can look at the slides for the other details. I'm not going to go over them. I talked about how you make sure the flow of air is uniform across the circular orifice at the end, this orifice right over here. This is very important for airflow calorimetry, because otherwise you get the wrong answer completely. You have to make sure it's well mixed, and he does that by measuring the airflow with at these 7 points across all these different power levels up to 5.5 watts. And I think he actually uses 4.5 watts during the experiment. And he also uses this other kind of anemometer, which is good to double check. Here he's installed the other anemometer halfway through the test, and the results continue about the same. Somebody else tried to do it and couldn't get an even flow of air. And this other person resorted to a different configuration. And then I talk about the wonderful replication of the original Fleischmann-Pons experiment done by Melvin Miles using a completely different kind of calorimeter here. This is very important because this was Fleischmann and Pons glass calorimeter, and this is the one that Melvin Miles developed. This has got two thermistors at two different locations. This is a copper jacket. The temperature of the copper jacket is the same everywhere. The two thermistors were the same within 1,000th of a degree, as I recall. And that means that mixing is not an issue, heat distribution is not an issue. It just removes all kinds of questions about the calorimetry. After he did this, he went to Japan and he used one of these calorimeters and he got very similar results. And you can read all about that. It's really great, wonderful. So then I talk about the difference between a successful replication and a successful replication, but no anomaly. That's what Mike McCubry often reported, where people said they got this, that, or the other result, and then he did the same experiment. He got the same numbers, he got the same conditions, but he always was able to explain it for prosaic reasons. There was no excess heat after all. That's a disappointment, but it is a replication. And then we have what Jean-Paul and others did with Mizuno's experiment, where they did everything they're supposed to do. The instrument's working, but they didn't see any heat. And then we have the non-replication where the instrument didn't work in the first place. Well, let me just zip over. This is Mizuno's reactor being used as a room heater. It's actually, in the real life, it has the bottle of gas and the power supply down here. And this is a wonderful slide that Srinivasan sent to me. And the paper is down here. You can click on this link. And you can also look at the Bark studies in cold fusion, which has a large collection of papers. And there's other references. If you download this PowerPoint slides, you can click on these links and see them more easily. Are there any questions?
Okay, so participants can unmute themselves and ask questions.
So you mentioned that airflow calorimeter is less accurate than water flow calorimeter.
Oh, yeah.
Has this been calibrated, the extent of error?
Oh, extensively. The papers that I list here describe how he did that. The most critical calibration, as I said, was the airflow rate, and that has to be done very carefully. That's the most variable thing. Also, unfortunately, Mizuno's laboratory has no air conditioning or heating proper. So the ambient temperature fluctuates tremendously, which means you can't even do the experiment for 3 months of the year. But the replication over at the University of Science is in a much better laboratory, and they can run it anytime, and their air temperature varies by about 1/10 of a degree. So that's much better.
And when Professor Biberian tried to reproduce it, he also used airflow calorimeter or some other?
I believe he used another kind. The problem is Mizuno has to use airflow calorimetry because his reactors are very large and it won't fit into any other kind of calorimeter. But I prefer something like a Seebeck or even a water flow with a large chamber or something like that. You have to use this kind with gigantic reactors like that. Nothing else would be practical.
Thank you.
Yeah. But by the way, people who look at this slide should then go to the end here and learn how to use the website I've got, because you can find papers a lot more easily than you might think. You can find there's many different ways of doing it, and there's this way of looking which Peter Hagelstein likes, and you can download all of the papers and use your own EndNote program, and you can add them to the end of your papers with links. You can do all kinds of great stuff.
I just want a quick clarification. You mentioned about anomaly or no anomaly. I missed what was the anomaly that you were talking about. Can you please
In this case, I'm only talking about excess heat. In these examples, there are others as well. Makubri was, as you know, he's excellent. He's very good at calorimetry, and he often reproduced people's calorimetric results and then showed that there was no excess heat. It just, they thought there was, but there wasn't. That's what I was.
Here you were
do you have any
doing
idea what?
with.
Go ahead, please.
I have a question. This was with the hydrogen gas or deuterium gas?
Mizuno's results. That was
right.
with deuterium.
With deuterium.
This is a nickel mesh with palladium rubbed onto it and then usually run in deuterium gas. If you look at our papers, he did run it with hydrogen and he did see a very small reaction in some cases.
So deuterium performed much better than hydrogen, no?
I think that's usually in almost all cases. Yeah, the one I showed you, the spectacular results at the beginning here, this was with deuterium. Back at the beginning here. Whoop, this right here, that's deuterium. And then there's some other problems I have with it, which I described in the paper. The output with Mizuno's experiment was very stable at times right here, extremely stable. Frankly, that's too stable. I think that makes me nervous because I think it might be an instrument artifact. But then occasionally it started fluctuating around like that. That looks more like a cold fusion reaction to me. This looks like the instruments got stuck at some power level for some reason. And the replication is also very stable.
So was transmutation
changed from one?
No
Raj,
one
go
has
ahead,
been able
please.
yeah. So was transportation also looked at in these experiments?
No, not at all. Sorry. Unfortunately, Mizuno's instruments were destroyed in an earthquake, and he hasn't had an SEM or other things. The university has those instruments, and I hope they will look. The only person working on it now is Professor Muto. The others, the undergraduates graduated. Professor Muto couldn't work for most of the year because of the pandemic, and then he couldn't work because he broke his leg playing rugby. Which is remarkable because he's 72 years old. And as I said in my talk, I don't know whether that's admirable or stupid, but it's emblematic of the field because 72-year-old people should not be playing rugby. And it would be better if we had much younger people doing these experiments. That's my opinion. Most unfortunate.
Other questions? I had a quick question actually. What produces change? I mean, in one case it's stable, in another case it's not stable. Is there anything, any conditions that change, or is it just?
It was a new mesh, and I think that they tend to be somewhat less stable when you first install them. It says R21, that's the reactor number 21 new mesh. He just installed it, and it did nothing for a while, and then it started fluctuating around like that. I don't think it ever stabilized, but if you look at that graph carefully, you'll see there's some kind of periodicity there. On, off at over a period of several hours. The paper that this comes from, you can read it and see for yourself if you'd like. But this one had been in use for a very long time, and it seems to get more stable over time.
What was the temperature at which the mesh was kept?
The pressure very low. That's one of the interesting things. Initially, he pressurizes, depressurizes, cycles it through many times, and he looks at the gas coming out of the reactor to see if there's contamination. And then when it's coming out very clean, then he pumps it way down almost to a vacuum and runs it, and that's when it produces heat.
No, the temperature.
The temperature is fairly high. It's in the papers. I've forgotten offhand. I can look it up. You see, I should have all this stuff at my fingertips. Let's see. You want me to look it up, or you want to just move on? To look it up, I go to my website and bring up the papers, or I can do it from here. See what happens if I do it. This is how you, if you get the original paper, you can do things like this. But it came up on the other screen. See what happens. Link to the other paper. It's very hot when he's cleaning the reactor, and it's like the input power is 240 watts in some cases, 100 watts. It ranges from 50 to around 250, and it's a, as you see, it's a metal cylinder, and that's inside of it, so it's quite hot, 300 degrees.
Now you said the pressure inside the chamber was extremely low.
Very low. And when it started, he thought it would have to be high, but he gradually lowered it, and the lower he got, the better it worked, which was something of a shock.
So the heat inside the generated in the mesh may not reach the, may not reach the, let us say, the container. Right?
Oh, well, no, the mesh is inside and the heater's inside as well. The mesh is right around the edge of the inside wall of the reactor, and the heater is smack in the middle, so the heat reaches the mesh before it reaches the walls. So there's no doubt it would be the hottest part of the thing. He measures the temperature of the reactor wall on the outside, as well as with the thermocouple rights in the very middle as well, and they're pretty close together. So the reactor wall temperature is the same as but then the whole thing gets hotter when there's excess heat. And in the case of the 50-watt reaction I showed back there, it's much hotter. Let's see. This is the very oldest.
Any further questions?
Yeah.
Thanks. Any further questions?
The heat treatment beforehand is, as I said here, 100 to 120 watts to free up the contamination.
Okay. I don't see any other queries. So thank you, Jet.
Thank you.
Perhaps we'll move on. Thank you very much. So the next talk is from Vladimir Vysotsky. So Vladimir, please share your screen. Yeah. Okay, thank you. We can see it. So please give a brief introduction to the talk, and then we'll open it up for questions. We can't hear you so far.
Okay.
Yeah.
Thank you.
Yeah, right. We can hear you now.
I'm here.
Thank you. Yep.
Yes. Thank you for the invitation to be here on this meeting related to my friend, Dr. Srinivasan. I would like first talk several words about I met Chino for the first time about 30 years ago at the first conference that was conducted under the Steve Jones in Provo in Utah. This was very, very interesting. It was very young. We also were very young at the time. It is photos of my friend. It was a great scientist, very great optimist, and wonderful friend. We will always remember him. It is very interesting. He organized the conference that was in SRM University, first workshop on the biotransmutation. It's very interesting. Also, it was leader and organizer of such conference. Also, briefly, I would like to inform you about my presentation. Presentation has a very wide interval diapason from initial laboratory experiments up to a scale of Earth. was very interesting. Now there are two words. It is a word, biology word, biota, and nuclear word. It is a terrible word. It's a word of atomic bomb. It is a nuclear reactor accelerator. It's a very interesting. Is there any bridge? Of course, there is very long history. My friend Berian very detailed describe the whole person who's most important was the Louis Kervan also. And we starting our investigation about 25 creation of his most interest for us was Bauer isotope iron 57 because me and my friend Alla Kornilov were related to the nuclear processes, and also it is there is very precision method of Bauer spectroscopy because it was main reaction from which we have started our investigation creation of iron 57. Next was creation reactor of not only with little light isotopes by middle mass isotopes, for example, creation iron 57. And for historically, next step was a creation of heavy isotopes based on the cesium-130C transmutation stable isotope cesium to another isotope barium-134. Of course, it is important for us because first of all, first point, it is a heavy isotope, is very interesting, and another more important, it is an isotope very similar to radioactive cesium-137. So very important method of optimization of such reaction transmutation in biology system. It was a possibility of using not usual so name online culture, simple culture similar to Escherichia coli, because the efficiency of reaction with participation of such microorganisms is very small. And we have using the very specific microbiology association, syntrophic association that consist from many thousand different cultures that are in the state of total symbiotic. That is symbiotic system. It's very stable to action of any aggressive condition. It's possible. It is system can live at very high acidity, for example, at very high level of radiation, so on. Such transition from online culture to synchronization, by this transition, it is possible increasing the efficiency of reaction by about 2 orders of magnitude, 100 times. For example, it was typical experiment creation of iron 57, does the magnitude of Mös-Bauer resonance about 0.1%. And in such culture, microbiology culture, magnitude or deep of such resonance is several percent, for about more in 30%. In fact, we have increasing by 100%. And also next step was creation of transition to, it is some description of experiment of transmutation of cesium to barium, of course, very interesting. So we have observed the in time decreasing of the initial concentration of cesium and synchronized decreasing, synchronizing, increasing of concentration of barium, and very great efficiency of such transmutation. And of course, main aim of our analysis, what is the application of such method of transmutation of isotopes in biology system in related to the radioactive isotopes, because it is the most important process, product. You visit the Chernobyl, it is Hiroshima, well-known pictures, it is Fukushima.
I think we have lost him.
50 tons each day. It's thousands, 100,000 tons of territory around the Hiroshima station. It is
His connection is very poor, I think.
Yeah. Vladimir, we keep losing you in the middle. Okay. Please,
The screen is also
Vladimir,
gone now.
you're muted now. Please unmute yourself.
No, the screen sharing is gone. Pankaj?
Yeah, screen sharing, but he's there. He's there nevertheless. Please unmute yourself. Vladimir, please unmute. We can't hear you.
Pankaj, you can message him in the...
It was problem.
Yeah,
now is okay?
Right, thank you.
Yeah, but
Yeah, now okay.
Please
You
share
your screen again.
Okay. And okay. First experiment we have conducted on the base of radioactive water from contour of nuclear contour of atomic reactor from Kyiv Institute of Nuclear Research.
You need to share your screen, Vladimir. Share your screen, please.
Terrible. Screen, please. Yes, it's right. Right? Now is right or cannot?
No, we cannot see the screen.
Dr. Jerry, now is right my no?
No, the screen is not there.
No.
We can see you, but we cannot see your screen.
You may unshare once and share
why?
again.
Because demonstration to guest demonstration.
Yeah, now we can see.
Now
yes,
it's okay or not?
Yes.
Okay, thank you. It's problem is connection. Okay, right.
Yes.
Right. Okay. And also we have conducted experiment with initial very simple reactor, and for the first time we have observed acceleration deactivation of Lantan 130 and Barium 130 experiment. It is a natural decay. It is a change of radiation emission from our experiment. Of course, it is not very. This is not important isotopes because it is a isotope with not very long time, about 2 weeks. But most interesting step was the following: the analysis of the transmutation of cesium-137, because it's the most dangerous isotopes. It is a scheme of experiments, well known, and also we have observed. It is a very interesting first result. This result was obtained we have using the radioactive isotope 137 immediately from Chernobyl, on the territory of Chernobyl power station, because for such experiments we need clean isotope without admixture of stable isotopes, for example, cesium 133. And we have observed for the first time a very accelerated decrease of activity of isotopes that equivalent in most optimal case time of life increase from 30 years to 310 days, increase about several hundred times. And the different we have conducted experiment during last years, and most optimistic result for deceleration of cesium 100 water solution of cesium 137 about by 70% in 1 week, 1 week or 10 days, about very great decrease. It is not accelerated decay, of course. It is a transmutation of cesium, radioactive cesium, to stable barium, and it is lead to decrease of radiation emission from closed flask with such isotope. It is very important, of course. It is some biophysical reasons, because what is the reason of such process, of course, but in our opinion, it is not specific biology transmutation. No, it is a usual physical process, but this process is very accelerated under some specific properties of growing biology cultures, because biology culture is not stable system. It is a system with a very intensive internal development, with growth, with formation of different structural elements, formation of dynamical nanotracks. In all this case, it is possible, in according our calculation, in our opinion, it is possible very accelerated, very suppression of action of Coulomb barrier to that process. This model is related to the so-named theory of coherent correlated state. For example, if we have the standard for nuclear physics method of calculation of coefficient of transparency of potential barrier, for example, for a reaction cesium plus proton formation barium, the probability coefficient of probability of transparency is about 10⁻⁷ 2000, for example. It is effect zero, of course. But if you have using such a coherent correlated state, it is a state where particle is situated in potential holes in the state of coherent superposition. And if we can organize this quantum state that we have synchronization of fluctuation of all levels, in this case, we have the very sharp increasing of the amplitude of fluctuation. It is equivalent, there is a special coefficient of correlation. It is a modified relation of uncertainty, so I'm not a relation of uncertainty of Heisenberg, a relation of uncertainty Schrödinger-Robertson is the difference present of such root. Because if the coefficient of correlation R will be very close to 1, so the value of such right sides is in limit increasing. So fluctuation of pulse in such correlated state is very great. In this case, it's possible increasing the fluctuation, for example, in the typical systems that are situated at room temperature. It is possible increasing of fluctuation energy from very small part of 1 eV up to many tenths of TeV. So it is a coefficient of transparency in this case. Any low energy will be very close to 100% if we have created such correlated state. Of course, it is possible different method of formation such coherent states. Most simple, it is, for example, connected with the modulation of relation between wave functions, phase of wave functions of particles that situate potential hole. Its process takes place, for example, for increasing or decreasing of the size of potential hole. For example, if we have the process of increasing of size of potential holes, we have the following process of formation of coherent correlated state. Coefficient of correlation is very close to 1. For example, difference is 10⁻⁻⁵, 10⁻⁻⁶. It is very simple calculation. If we have, for example, increasing of the size of potential holes for typical biology diapason from 2 angstrom, for example, to 2000 angstrom, so the coefficient correlation is 0.99999, so on, and coefficient of transparency increasing from 10⁻⁻2000 or 1000 to about 4%. Fantastic increasing, and of course, in this case, it is possible very generation of very great fluctuation of energy, many keV. The same effect takes place if we have another direction of modulation of potential hole, decreasing of size from large size, decreasing to small. Also, it is possible in this case we have the interference between different aging states of particle in the potential hole, and also of size, for example, several 100 times, and coefficient of transparency will be very close, very large. And such process take place in a biology system during national process roles. For example, the same process take place during cell division, for example, in the volume between two separated parts after process of division. It is a non-stationary potential hole there. The same process takes place on the surface of membranes, on the surface of mitochondria. Also, same process of formation of dynamical non-stationary potential holes of nano size takes place during DNA replication. For example, in this case, where we have replication DNA, it is a very fast and natural process. So many such processes take place. So it is very interesting. this description is related to the laboratory experiment. In fact, it's a LENR in laboratory tube. But our investigation during several last years were conducted in the relation to search of the possible natural application of such transmutation in the level of human body and in the level on the level of Earth scale. For example, we have investigated such process. I have discussed this work on the last ICCF conference. For example, it is a very interesting process related to the catastrophic result of procedure of formation of nether implant. For example, well known for implant using the titanium implants, metallic implant, but practical experiment dentistry showed that dispute is a very ideal condition of such experiments. Very often, medicine and patient observed very great catastrophic situation with implant. You can see these terrible photos. And also we have conducted such experiment because idea was the following. In oral cavity, there are many different microorganisms, very large microorganisms. Also, we have calcium as a part of the tooth and titanium as a material of implant. And also we have conducted experiment on the possible analysis of possible nuclear reaction with participation of natural microorganisms from oral cavity with in water solution, typical water solution, the presence of calcium and titanium implant. It is a typical, yes.
We're running a bit late actually now already. So could we just ask questions and we can go over more of this?
Okay, I have on 2 minutes. Yes. Okay. Please, possible.
Yeah, sure. Yeah, sure. Please go ahead.
Yes, I can continue.
Professor Wysotsky.
Yeah, please. 2 more minutes. Please go ahead.
Yeah.
Can I ask a question?
Yeah, please go ahead.
Yeah. Professor Wysotsky, the modification of isotopic ratios is one of the strongest proofs that there is something nuclear going on.
Yes.
But
yes.
have there been any attempts to replicate your results?
What results do you think about? What results? Results, for example, results related, for example, for transmutation of cesium-137 were repeated in South Korea about 2 years ago. Were repeated, yes. Results in India, for example, were repeated experiment on the transmutation of manganese 55 to iron 57. These last results, of course, is now new results on the. It's possible I can finish such description of the experiment with stomatology, with dentistry, and also we have conducted such experiment, and in result we have observed that after saving, after some saving of the implant, titanium implant, in the liquid tube with natural microorganism from oral cavity, they have observed creation of molybdenum. So it is reaction was titanium plus calcium in creation of molybdenum with positive energy. We have analyzed such possible reaction because there are many different isotopes of titanium, different isotopes of calcium, and different isotopes of molybdenum. And the criteria was the following: this reaction must be extra-energetic, of course, because in oral cavity is absent of source of very great energy. And second one, this reaction lead to formation of a stable, non-radioactive molybdenum isotope. It is because that according to our calculation and according to our practice of LENR experimental investigation, in any case not created radioactive isotopes. Of course, it is very simple calculation. I have published several articles on the description of such phenomena. So if I have analyzed all this possible reaction based on such very great number of different isotopes, and there is only one reaction. It is a reaction titanium 46, calcium 48, and formation of molybdenum-93. This reaction is positive energy release, 64 keV. Or another reaction, it is not correct because lead of formation of radioactive isotopes or need a special additional energy action. So because such reaction take place, and we have the creation of molybdenum, in generation of energy 64 keV, it is not very large energy, but such formation of such energy lead, according, for example, to the analysis of Peter Hagerstein, lead to formation of ultrasound vibration of light magnitude with frequency is close to the about 10 power 13 Hertz. It's lead to the destruction of calcium and of course of destruction of fused matter. So very simple method for stopping such process. It is using titanium without such isotopes. Because it depends only from one isotope. Titanium 46 is natural concentration in about 8%. If we have titanium without such isotopes, in this case, it's possible to create most optimal titanium implant. Such reaction is absolutely not will be possible. Also, it is some description, microbiology description, so one of such reaction. And also, next step, we have two steps from laboratory tube to human body, medial level, and mega level. It is related to the such phenomena that was created on the Earth scale. It is well known, there is so named ferromanganese crust and nodules. It is well known geological objects that has a following view. It contains from the very great concentration of iron and manganese, about 40–30%, and also very thin layer, thickness of such a layer from several millimeters, maybe 1 to 3 millimeters. It is for typical photos of ferromangan modules. And also, very interesting, there is some special institution in Switzerland, in Lugano, I don't remember, in Switzerland also, and such institute that related to the analysis of isotopic. And such were conducted during about 10 years. Scientists from such institute were investigated the properties of such geological objects in different places of oceans. You can different place, ocean, Pacific, so on. And very interested in all this point, all objects have the, you can see the sign of such, it is a change of concentration of iron 57 to 54. In all cases, we have the decrease of concentration of decrease of 57 in relation to 58 in relation to natural contents. It is very strange. Why? The same effects per experiment were conducted with isotopes different, relation of 57 to 54. So in all cases, we have decrease concentration 57 isotopes iron in relation to 54 and in relation to 56 in all point of ocean. Without all this case, it is 100 points. Why? What is the reason? And the analysis was very simple. Yes.
I think maybe we should go into discussions because people have seen the talk already. So we don't have to go through the talk and completely. That's the point actually. So otherwise we'll run out of time because
I have only 2 slides and they finish.
Now, another possibility is the session 4, you are presenting a talk, right? We can continue for greater discussion.
So, yes, right. So in the result, following the all these processes and the anomalies of the concentration of relation of 3 isotopes, iron 57, 54, and 55, is connected with usual transmutation, biology transmutation by the reaction that we investigated in laboratory tube. So in water, there are many concentration natrium and phosphorus and creation 54. there is many concentration of manganese and natural protons, 56, but very small number of deuterium in water. Because such reactor is practically not possible, by this reaction increase the concentration of such isotopes. So it is very interesting results. If we have calculated what the total mass of created isotopes 54 and 56 in by the biology transmutation of natural microorganism on the deep of ocean and sea, we have the following results. Each second, microorganism created about 6,000 tons isotope each second. It is about 100 times more than all plants that related to creation of iron in the world. It is a global scale of in a planetary scale. It's very interesting. So no, it is some calculations so on. It is my report is I would the aim of my report is the following. I would like to show that process of LENR in natural condition takes place on all scale, from the micro level through the nano level to the macro level up to the mega level to the planetary scale. So it is a very important, it's a very interesting for subject of future investigation. Thank you.
Thank you, Vladimir. Very interesting. So I guess we can have some questions. Questions, please. I know we are running late, but let's still, ask some questions. We still have some time. We can go into the discussion and we can have discussion some other time.
Okay,
also.
okay,
So
okay.
please.
Thank you.
Yeah. Any questions?
So there
Well,
was
maybe
a
I just want to
question.
make one quick comment actually. See, you presented a certain model. The model basically amounts to a time-dependent potential. Now, when you have a time-dependent potential, then there's a standard quantum mechanical procedure to do calculations. And in fact, we have utilized that actually. And in the paper that I am going to present, we have in fact gone through that in great detail. And so it's actually, I mean, you can't, I mean, it requires actually quite rigorous calculation.
The modification of potential not related to increasing.
See, what you're doing is that you're basically proposing a time-dependent potential. You're saying that the potential is decreasing, is squeezing. As I understood the talk, you're saying that the potential is decreasing, is getting squeezed.
No,
and that's a time-dependent potential.
According to the theory of quantum mechanics, we have not increasing the potential, increasing or decreasing potential. We have only modification of the width of the potential hole, increasing width,
That's
not
what I mean.
magnitude.
That's exactly what I mean. So the width of the potential changes. So that means you have a time-dependent potential. So
time-dependent potential.
Then you have a standard quantum mechanical procedure to do the calculation.
Yes,
and that's exactly what we have. Yes.
Yes, right. The idea of the formation of coherent exactly correlated state was created about.
So can I just continue? So that is exactly what we have done in a very rigorous way using a second-order time-dependent perturbation theory. Now that actually we could make it work, but it doesn't just work by itself. In fact, you need something more. So by itself actually will not work. You need something more to make it work. And that's something I'll explain in my talk. What exactly you need to
all calculation.
Yeah.
Yes. All calculations were made on the base of standard. I don't understand your question. All calculation based on the standard quantum mechanics. Absolutely standard one. Where this analysis was conducted for the first time in 1930, about 90 years ago, by Schrödinger and Robertson. It is a typical analysis of the state of particle in non-stationary potential hole. Non-stationary, because of is the result of modification of potential hole, the process of interference. Yes. Non-stationary potential hole, yes.
Okay,
Yes,
let
right.
me just go through my talk, then we'll discuss this further. So are there any other questions? Okay, if there are no further
What question?
questions, let's thank Vladimir for this very interesting talk. So we'll move on. And
Okay.
Even, I mean, in session 4, we can also take up questions again on this talk, because you'll be giving
right.
another talk, right? So, because I'm sure there are other questions, but we can take it up again in session 4.
Yes, right.
yeah, so okay, so we'll do that. We have a full session for tomorrow, so we
Yes.
can have questions on this talk tomorrow again.
Okay.
So yeah, so thank you again. So I request Thomas to please share his screen and give a brief introduction to the talks, and then we can start discussions on the talk.
Oh. Так, стоп, я куда-то делся.
Okay, is the audio working okay?
Yes, it's working fine.
Very good. Stand by.
Yes, we can see your slides.
Good.
So over to you.
Okay. Well, first, let me say thank you to the organizers of this workshop for the opportunity to report on this project that I did with Dr. Srinivasan. I know most people call him Chino, but he let me know as we were doing the project that he really preferred Srini. So I doubt if we're going to change from Chino, but I will call him Srini in this talk. The talk is actually posted, of course, on the website and on Slack, I think, as a video. And so my purpose here would be to just give a very brief introduction of what's in the PowerPoint slides, and then open the floor, so to speak, to questions. So this is, of course, the cover slide. It's Dr. Srinivasan was certainly a pioneer in the field. And what I'm going to do now is I'm going to go very quickly just to let you know what's in the presentation, so as to leave time, or maybe make up some time, or leave time for some questions. So this was a project that I did with Srini as part of a larger effort, the LENR Research Documentation Initiative, which Dr. Srinivasan, Srini was probably just the third in the now 26 participants in this overall initiative. And it began with a pilot project that I did with Ed Storms. And then that was reported at ICCF 21 in Fort Collins, Colorado. And it was during that conference that I had a conversation with Srini proposing that we do a project for him. And that's what led to this project. Here's a nice photo. I think it was taken at ICCF 16 in Chennai, but I'm not absolutely certain. Okay, so here are the components of the project with Srini. The most important part, I would say, or certainly the salient part, is the research autobiography that he provided. He actually authored it himself, consisting of 6 phases, including the first phase, which was his pre-LENR era. He was, of course, at the BABA Atomic Research Center for many years before the 1989 cold fusion, cold fusion announcement. The other components are 3 interviews, one of which I did, a collection of his reports. There were 45 of them when we first got them listed, and then for the most part, he provided them, and some of them came from Jed Rothwell's Leonard Canner Library website. There were some related documents that he provided that he did not author himself. And then finally, we did prepare a report and consisting of 2 volumes, the second volume being the actual copies of the publications. So here are the 6 phases. I'm not going to dwell on these, just to let you know here the time ranges of each of the 6 phases as he identified them. Again, phase 1, pre-cold fusion era. Phase 2 was really where he did most of his cold fusion research at BARC, resulting in this very important publication. Phase 3 was what he called his silent decade. He had been at BARC from 1957 to 1997 when he retired, and it wasn't until 2007 that he became active again in the field. But he did stay in touch with his contacts and attended the conferences. And then here's phase 4 was his fresh attempts. He got interested in revitalizing cold fusion research in India as a result of the ICCF 13 conference. And he really accomplished a lot, including organizing and chairing the ICCF 16, which took place in February 2011. Phase 5 was really focused on the Rossi reactor because he was very interested in nickel hydrogen systems, but like many of us, he was very disappointed in the outcome of the 1-year test with industrial heat. There's a quote there, there in bold in his actual reaction to that. During this time, he also published a special section of Current Science Journal with Andrew Millenberg. Then in the last phase, he made a final appeal to the politicians for intervention, and that resulted in his coordinating funding for 4 LENR research groups, one of which, of course, is IIT Kanpur, the sponsor. Thanks again to the people who organized this workshop. I did an interview with Srinivasan, Dr. Srinivasan, at ICCF 22 in Italy in September 2019. There were 2 earlier interviews. I just got permission from Russ George and Marianne Macy to include these interviews in the public part of the report that we'll be coming out with. Here are the highlights of the 2019 interview. There's a picture of, not a very good picture, of Srini at the ICCF 22. There are several highlights in the interview. Then there was the collection, as I said, of his reports. Most of them he provided, some of them we got from the LENR Canada website. They're in volume 2 of the report, which is pictured here. Other references to his work were in Malov's Fire from Ice and Huizinga's Scientific Fiasco and some others. These are the project reports. There were 3 versions of volume 1, most recent in June of 2020. We identified some future opportunities, as we usually do in the LRDI, to expand the interview to include the subsequent phases. In the Assisi interview in ICCF 22, we were only able to cover phases 1 to 3. Anyway, I won't go into these other opportunities. Needless to say, we weren't able to get to them because of Srino passing last year. These are the main accomplishments that Dr. Srinivasan pointed out. The first to discover, he felt, the neutron to tritium ratio anomaly. He did the statistical analysis of the neutron emissions and the use of audio radiography, which demonstrated the localized nature of tritium emission and therefore of the actual LENR reactions. So here's a summary. Research pioneer in the field, one of our earliest contributors. At the time, 1989 to 1990, he led one of the largest research efforts, which was at BARC. Prepared many publications, was responsible for a number of advances, certainly became an international presence in the field in a large part, I think, or certainly a significant part, because he was so easy, personal and easy to work with. A few more words on the initiative itself, which I've already said. The pilot project was with Ed Storms. It was reported at ICCF 21 as a poster. Here's some more information on the LRDI. And I'd certainly like to, in addition to the organizers of this workshop, I'd like to thank Carl Page of the Anthropocene Institute for support in for the expenses of the project, well, of all of the projects under the umbrella of the LRDI. And I'd also like to thank Ed Storms for being such a good collaborator and for serving as the pilot project. So now's the time for questions. So I'll discontinue.
Thanks, Tom.
So I hope that
Thanks, Tom.
that quick review. Of course, the full presentation is available on the website as the organizers set it up. So open for questions at this point.
Thank you. So yeah, please go ahead and unmute yourself and ask questions.
So thank you for this, Rajpala. So today morning you sent a set of papers. Thank you of Dr. Srinivasan. Thanks for that. So I was just wondering whether you showed some folders, right, of papers and so on. You're planning to digitize all of them and host it in some website, or what is the plan?
Well, I believe the ones I made available to you are all in PDF form.
Yeah.
So they're all, I think, they are digitized. And if you're certainly welcome to put them up on the website for this workshop. I'm currently figuring out the best way to, well, there will be proceedings for this workshop, and I think that would be a good way to quote unquote go public. When I do these reports for the participants, they're always confidential between myself and the participant, unless I get permission. And so I'm quite sensitive about that. And I'm sure that Srini would really want to have his work made as widely available as possible. So please feel free to put the papers up on the website if feasible. If not, I haven't decided. I may create a special website or some other measure.
Thanks.
Why don't you give them to me?
I think I did load them up on a Dropbox folder, and I made arrangements for an email to come from Dropbox to Raj and Rajiv for access to that folder.
No, why don't we put them all at leonardkenner.org? Is there any reason why we would not do that?
If you want to do that, I would absolutely be in favor of doing that, Jed.
Sure. Okay.
I think there would be some overlap, of course, of what you already have on your website, but I think the 45 papers may include some that aren't there yet. But please, let's talk after this meeting and make arrangements to put them up there.
Sure.
I was also wondering about your other projects. You were saying that Dr. Edstrom, all these things, everything is going to be uploaded somewhere, or?
That depends on the participant. It is my plan at some point. I mean, the initiative is still very active in securing additional projects with more of the LENR researchers. For example, most recently, Dave Nagel and I have talked to Avid Lomax about the possibility of documenting his research or his contributions to the field. But at some point, I hope to prepare an overall report with a summary of the findings of each participant. But my initial objective here was to just get the information and document it and to report it and then decide later on how best to present the results to the outside world, so to speak. But currently, the information is confidential between myself and the researcher. And you can imagine that people, would be more willing to participate in a project if they have assurance that that their material isn't going to just be made public. So I have to be quite sensitive about that.
I think it is best that these are put up on LENR.org with Jed Rothwell.
Okay,
Because I think
very
it is,
good. That's what
it is
we'll
the
do then.
repository.
Thank you, Jed.
And Raj, I suppose we have made it available at the website, right? At the workshop
Not
website?
as of now, because I was not sure about copyrights and so on. I thought we will discuss and then we will do that. Right now, it's in the Dropbox folder. Yeah, we can decide. We'll do it soon.
I think we should put it up as soon as possible. I don't think there are any of these, intellectual property issues or something.
Yeah, at a minimum, I suppose you could go ahead and put up the list. I think I sent the Word document that has the list of the publications. You could put that up if just to list which ones are included in the collection.
Yeah, we'll do that soon. Thanks.
Any other comments, questions? I was just curious to know, what is your company involved in? I mean, what does your company do actually? You said you are.
Yes. Okay, so I'll give you a kind of a historical answer. My interest in the field goes back to about 2005 or 6. After having my advanced degrees in geology a few decades ago, I got interested in public policy and in particular in energy policy. So I went back to school and got what's called a mid-career master's degree in public affairs at the LBJ School of Public Affairs here in Austin. And I wrote my thesis on public policy and cold fusion and the terrible situation we're in that everybody on this call is quite well aware of regarding public support for cold fusion research, and also for doing some advanced preparation for the tremendous secondary impacts and unintended consequences. So I became very interested in public policy for both of those things, developing the phenomenon, gaining the energy and other benefits on the one hand, and then dealing with the impacts on the other hand. Both of them very cogent topics in the field of public policy. So that was really my start in the field, and it's still, I guess you might say, my first love. I've been giving presentations on cold fusion and public policy and the various aspects of it almost since 2005. I'm really beginning with my thesis in 2008 and co-authored with Ed Storms and Dave Nagel and so forth. And then I got interested in doing this documentation subsequently. So those are the two main things that I'm doing at this time. I hope to give another presentation on public policy at the upcoming ICCF 23 conference.
Thank you, Tom. So if there are any other questions, please comments, questions. We raise now.
Okay, thank you so much again to the organizers.
Thank you.
I had no idea, of course, that this excellent opportunity to present the work of Dr. Srinivasan would emerge, and so I'm very thankful for this, and I appreciate the opportunity to participate.
Thank you very much for this very nice summary of Srini. I guess he prefers to call himself Srini's work. So thank you very much. So we move on now. So the last talk for today's session is by Peter Hegelstein. So I request Peter to please share his screen. Yes. And give a brief summary of the talk. Yeah, we can see the screen. Yes.
Hi.
Yeah, we can hear you. Yes.
Okay, so I had some slides that were in the nature of an introduction. So that's what I presented. I'm not sure that it's productive to go through all the slides because during the video it was like 38 minutes or something of presenting over 100 slides. And so the application of this was for new people approaching the field to try to understand something about a perspective on excess heat experiments. So I'm primarily a theorist, and my interest in the issues concerns, well, basically, is it real? And if it is real, then how does it work and why does it work? And can a theory be put together that would be both defendable and workable, calculatable? So that's what I've been involved in. So in the slides, one issue was what is the effect in the first place, focusing on the energy effect, namely there are many other aspects of it as well, including transmutation and tritium production, low level energetic particle emission, and so forth. Some questions: how do you study it? How do you make conclusions about what's going on? So people measure helium. You can get information as to what energy the helium is born with by looking at the neutron emission. Other issues is excess heat is correlated with loading and with current density and with temperature. In the case of helium, the question has to do with the energy. Is the energy associated with the helium? If helium is measured, is the amount of energy detected correlated quantitatively? If the reaction is going to be 24 MeV, do you actually get 24 MeV worth of energy for the helium that you see? And in the two experiments where the helium was scrubbed out of the sample, the answer is more or less yes to within 10% or so. Lots of other issues. How do you trigger it? What's involved in triggering? Why is it triggering? Why does the effect get triggered? According to my models, vibrations are important, and triggering mechanisms appear to be mechanisms which produce vibrations at very high frequency, for example, in terahertz frequency. There's some experiments which are very telling in this regard. The LETS 2 laser beat frequency experiment. The beat frequencies that seem to be best at producing a response are the frequencies at which the velocity of the vibrations is close to zero. So once you put the energy into the vibrations, they stay there. Mitchell's experiments, the Stokes and anti-Stokes line, if it's real and can be confirmed, is ridiculously important in connection with this. That in his system, basically, unless you had a phonon laser, you wouldn't have seen anything whatsoever. And my models for some time have been consistent with there being phonon laser effects. So the nuclear energy goes into vibrations. Let me stop babbling here, and in the interests of time and discussion, let me entertain comments and questions.
Thank you. So now the talk is open for questions. So please unmute yourself and any comment or questions.
Professor Hagelstein, what made you, conclude that the phonons are playing a big role in this in the LENR phenomena?
A good question. It actually started out on theoretical grounds, namely, I was looking at the nuclear system as an equivalent two-level system with D2 being an upper state and helium-4 being a lower state. And then the question is, where does the energy go? Now, if it was an incoherent process, then the energy would have to go into energetic nuclear products. But there are no commensurate energetic nuclear products seen in the experiments. So, okay, then where else can it go? I mean, theoretically, you've got photon channels, you've got phonon channels, and you've got basically electron channels. And that's it. And if it were in photon channels, by now we would have seen it, or certainly by the first year or two, we would have seen it. And there was no sign of it at all. And so that left vibrational channels and then electron plasma degrees of freedom. And over the years, initially the theoretical problem in connection with the phonons was vastly simpler and vastly cleaner. And over time, it seems that there's substantial evidence that the energy goes into the vibrations, but there's also evidence, indirect evidence, that if you excite electronic degrees of freedom, that can trigger response as well. So my focus is on the vibrational thing, largely because it results in a vastly more straightforward theoretical problem model to put together and to analyze. Although I have nothing against having the electronic, basically electron plasma degrees of freedom being involved both for stimulating and for accepting some of the energy. The issue is that the electronic degrees of freedoms tend to decay extremely rapidly, femtosecond time scale, whereas terahertz phonons can decay in a picosecond or slightly longer time scale. And that difference is, to me, extremely significant and makes the phonon problem vastly more interesting.
I was intrigued by your that steel plate experiment. The steel plate which was vibrated and on top of which some radioactive material was kept, and it was found that this, I think that there was anisotropy in the radiation emission, right? So what was the conclusion of that? I mean, what did you conclude from that experiment?
Okay, so those experiments continue, and the hope is to basically write them up in a number of papers for mainstream journals. But there are several conclusions. One conclusion is that it's possible to get reproducible dynamic effects, including angular anisotropy on the 122 and 136 kV gammas. We've seen evidence for delocalization on the 14.4 kV X-ray or gamma, depending on how you like to think of it. The question, given that each excitation transfer, if it involves terahertz vibrations, can proceed no further than a few hundred angstroms. And as a result, and in our experiments, we have evidence that the excitations transfer has moved excitation 1 to 2 millimeters, which implies 100,000 to 200,000 excitation transfer steps within the lifetime, the 100 nanosecond lifetime of the 14.4 keV line, if that's the transition that's responsible for the excitation transfer. Now, the issue is that we since we haven't seen angular anisotropy on the 14.4, and if the excitation transfer happening on 14.4, that in principle should be the easiest place to see the angular anisotropy. Now, one possibility is that it happens so fast that we go into a basically non-resonant excitation transfer regime, which spoils it. So that's why we can't see it. Another possibility is that maybe the excitation transfers happening, transferring the excitation 136 kV. And at the moment, Florian's trying some experiments to try to clarify whether that's the case or not. Anyway, I remain convinced that the experiments are very foundational, a very fundamental, a very important experiment. And I'm of the opinion that this phonon-induced nuclear excitation transfer provides a theoretical foundation for excess heat and for essentially a large majority of the other anomalies. Essentially, most of the anomalies in the field, with the exception of the EVOs, which I think Lutz Yaitner's ideas are more relevant to.
Thank you.
Okay, other questions?
Yeah, Pankaj, I have a question. So, so are you of the opinion that there is a unifying model for excess heat and nuclear transmutation, or there are many operational mechanisms?
I think that there's one underlying model that is going to apply to excess heat production, tritium production, helium production, transmutation, collimated X-ray emission, our excitation transfer experiments, the low-level nuclear emission, the energetic alphas, energetic neutrons, energetic protons, that kind of thing. So yeah, I believe that there's one basically straightforward, let's call it a discipline that is founded on a coupling between vibrations and internal nuclear transitions. That combined with basically not quite standard, but almost standard models for coupling of two-level systems with oscillator. I think these ideas can will be able to quantitatively account for pretty much all of the observations. In earlier passes at our models, if we assumed that the down conversion of 24K MeV quantum was not rate limiting, and we were able to estimate a rate for excess heat production, which is, within the realm quantitatively of being in agreement with experimentally observed, without having to require orders and orders of magnitude of screening or anything remotely like that. So yeah, I think we've got our hands on a model that's going to be relevant to the large majority of anomalies that have been reported.
But would such models also be applicable to the soft condensed matter system, like these biological transmutations and so on?
Well, yeah, yes and no. Some of the effects that have been described by Vysotsky certainly have a place within the models. and the idea is certainly biological systems. If you think about it, they transfer energy. They convert either sunlight or radiant energy to chemical energy, or in some cases, convert chemical energy to to do internal biological work. Now, when that happens, some of the energy gets dissipated in vibrations, and so there's a mechanism to produce vibrations, and if for the vibrations to be driven, for basically terahertz vibrations to have a source to get them going, potentially means that you have the possibility of drawing down the nuclear energy into those vibrations and making things happen. So the biological problems are in general much more difficult than solid state or basic nuclear physics problems. But I'm optimistic that the models will be relevant to what Vysotsky's been describing.
Thank you.
Other questions, comments? So in your model, I mean, may I ask a question? In your model, how do you actually manage to evade the Coulomb barrier? How does the Coulomb barrier get evaded?
Oh, in my model, the Coulomb barrier is I basically am pretty happy with the Coulomb barrier. So in the low energy DD collisions, there's evidence for some screening, and in connection with those experiments, Chursky and Hook and so forth, they've done some estimates for Thomas Fermi screening lengths and the associated screening energies. So the screening energies, basically by doing the best modeling that they can do, as I recall, is somewhere in the neighborhood of 130 to 140 EV. In their experiments, they need higher screening energies to be consistent with the data, but I think there are dynamic effects in the experiment that a static screening model doesn't include. I think in the experiment, a deuteron can get closer to a palladium nucleus than you would get normally on average in a static system. So the issue has to do with how the gamma factor associated with the Coulomb barrier comes into the problem. So if you do incoherent fusion, then the reaction rate's proportional to the square of the matrix element. So the gamma factor comes in twice. Your rate's proportional to e to the minus 2g, where e to the minus g is on the general order of 10 to the minus 35th or thereabouts. In a coherent, so in quantum mechanics, you can have incoherent processes where a single state decays to a continuum, and golden rule, Dirac's version of the golden rule, it's attributed to Fermi. It's called Fermi's golden rule, but Dirac was the one who derived it first. But the golden rule is proportional, the rate's proportional to the square of the matrix element. So the gamma factor for an incoherent fusion reaction goes like e to the minus 2g. From the models that I've been pursuing basically since 1989, the thought is to focus only on coherent processes. So in a coherent quantum mechanical process, the rate can be linear in the matrix element. So in this case, you get e to the minus g for a tunneling factor if you can achieve the coherent dynamics. So achieving coherent dynamics brings along its own set of issues and problems. But after very many failed models and unsuccessful attempts, a picture's emerged, which is both robust mathematically and appears to connect in unforeseen ways with quite a bit of experimental data.
Okay, I guess we can discuss more about, are there any other questions for Peter? Maybe I can just say a few more words actually. I mean, there are papers on the screening effects, theoretical calculations with regards to how much screening can there be. And those do not give you, very much screening effect at all. The screening effects that I see in the published in standard research journals is a relatively weak effect actually. So you are talking about, relatively large screening energies, which may be measured experimentally,
well,
but I don't see, being claimed theoretically.
okay, so if you have molecular deuterium, the screening energy is in the general vicinity of 25 electron volts. If you have deuterium in an insulator, again, the theoretical number, the experimental numbers in the general order of 25 volts. Like I say, the best Thomas Fermi screening numbers that I'm aware of are in the neighborhood of 130, 140 electron volts. And again, my myopic recollection is that that gives you somewhere in the neighborhood of 4 to 6 orders of magnitude of reduction of the increase in the gamma factor. So I'm, given that I was interested in getting most of the gamma factor back instead of having it be e to the minus 2g, e to the minus 1g, then 4 to 6 orders of magnitude out of 35, 37 orders of magnitude, logarithmically, it's not a particularly big deal. And so, 10 to 15% reduction logarithmically in the gamma factor was of interest. But if we have to settle for 25 volts, it'll be tougher to get consistent models. But I mean, the issue of screening is one which would be nice to get clarified. Towards that end, in my group and working with some other colleagues with density functional codes, we tried a series of calculations where we brought two deuterons close together near palladium or in monovacancy in palladium deuteride. And in those calculations, the density functional calculations, at least I'm familiar with, show no screening effect whatsoever, which is in itself also very interesting. So more work needs to be done to clarify how this works.
Thank you, Peter. So
good questions.
I mean, if I just understood your last point right, then that will be a big issue, right? I mean, if there is no the DFT kind of results, density functional simulation, if they don't show much screening, then this issue of Coulomb barrier will be significantly important, right?
Well, the models where the condensed matter models where screening come about are basically dynamical models in which the deuterons or other nuclei move in connection with vibrations, and they couple to the dynamical electron system. And when you couple those problems together, then you calculate dynamical screening in connection with vibrations. Now the density functional models are, in a sense, the question is, I'm wondering whether they're a little bit dumber than these coupled dynamical models, which means that in order to get the screening effects to show up, you have to do maybe you have to do a little bit different kind of modeling.
Are you saying that Born-Oppenheimer approximation is not valid? I mean, non-adiabatic dynamics, is it? Or
No, it's not. The non-adiabatic effects are pretty weak in general. On the other hand, electron-phonon coupling, lies at the basis of how vibrations interact with electrons and metals, and treating the vibrational system as coupled to the dynamical electronic system seems to be a pretty solid place to start to put together a model. And those models show the screening. So the point of my comment wasn't so much that the DFT codes seem not to show any screening, which means there isn't any screening. That's not the conclusion I'm coming to. It's that density functional codes, which we would like to use to calculate the screening, at least as far as I'm aware, nobody's gotten these codes to show any screening, which suggests that we're going to have to do our modeling a little bit differently to get accurate screening calculations done.
all right, thank you.
Good questions.
So are there any further questions? Actually, our time is already up right now. So let's thank Peter now, and we can close this talk for now. But we do have, so thank you, Peter.
Okay,
thank you very much.
Let me
so we
stop sharing my screen.
So we are supposed to have a discussion session, although time is already up, but we can actually use, maybe another 10 minutes. If there are any other further questions that people may want to ask, we can, have discussions if anybody would like to make a comment or have a question for any of the speakers, or any other comment that anybody would like to make. Actually, I have a comment for Peter. You said that no photons are seen actually in this experiment, so therefore photons cannot couple. But if photons are produced, won't they have a small mean-free path, and they will be buried inside the nuclear, inside the medium somewhere? Peter?
I'm sorry. I have a boiler going on behind me, and I can hardly hear anything.
Okay.
Can you
Sorry.
either shout the
said
question or write it in chat or something?
You said that, okay. Yeah. What you said was that, it cannot be, the energy cannot go into photons. Therefore, it has to go into the lattice. But my point is that if energy goes into photons, let's say you produce a gamma radiation, the mean free path of gamma radiation may not be very large inside the medium, the medium we are discussing. I had to check this actually, how much it is. And it may just, transfer the energy to, lattice sites, basically to phonons. So the energy may get transferred through photons to phonons. Is that possible? Or that is ruled out?
So that question came up certainly in 1989 and has been the source of intense discussion for decades. My perspective on this runs more or less as follows, that if you're producing a watt of excess heat, that means you're going to get, if you're making gammas, and if they happen to be 24 MeV gammas, that means you're going to be making like a lot of them, in excess of 10 to the 11th per second. Now, a 24 MeV gamma is sort of easy to see in an experiment. If you've got a sodium iodide detector that's thick enough and big enough and so forth, then you can you can detect it. And there have been, you know, a small number of experiments where appropriate detectors were mounted near a cold fusion cell, and basically in none of the experiments was there even like a single I mean it's hyperbolic to say that there's not a single hyperbole to say not a single 24 MeV gamma was detected, but you would be able to detect gamma emission at rates of 1 gamma per minute pretty easily. And even such rates are not consistent with the measurements. So then there's arguments about if you've created a 24 MeV gamma, what's the mean free path? And unless there's some enhancement of the interaction or so, basically, essentially all your 24 MeV gammas leave the experiment easily unhindered. Perhaps they bounce around a few times on their way out, but they don't get absorbed. So another issue is that if any significant fraction of your 24 MeV gammas at the watt level made it out of the experiment, it would be lethal to people in the vicinity of the experiment. So from my perspective, I basically cannot I cannot see. I mean, there have been probably half a dozen theories proposed over the years where people started out saying that the first step of the reaction is to make a 24 MeV gamma, and then the 24 MeV gamma interacts very, very strongly with the medium elsewhere. So this has been tried at least half a dozen times over the years. And from my perspective, it's just there's just no way to basically do anything with a gamma once it's been created. So my interest has been in models where the gamma does not get created in the first place.
Thank you, Peter.
Can I just have one last question? Yeah. So, Professor Halson, just one more clarification. If I understood your model right, the energy released is somewhat taken in by the phonon degrees of freedom, and which in turn is used for further nuclear reaction. Is that the way to think, or?
So the way the model works, so that during the past year, there's actually been some modification in my thinking about the model. Basically, the idea is the first step of it is that 2Ds make a transition to helium-4 with the exchange of one phonon, terahertz phonon, and the excitation goes elsewhere. So now the question is where does it go on the first step? And the thought is it depends on the host lattice, that in the case of 24 MeV, excitation energy to transfer, if there happens to be some basically relatively low loss state available close to 24 MeV in palladium, then that could take it as a very temporarily, transiently as a first step. Then the thought is another possibility is maybe it down converts to 2. So if it down converts to 2, now you have to find a relatively long-lived state near 12 MeV in palladium. And in this case, I think probably that's a little bit more likely. And if that were true, then you might expect a low-level alpha emission. If I'm not mistaken, somewhere in the general neighborhood of 4 to 8 MeV. And there's actually some evidence for such low-level alpha emission, which, if this interpretation is true, would tell you something about the energy of some of the reasonably long-lived excited states. But anyway, it goes through these excited states very, very quickly. So even though so in our excitation transfer experiments, if we've got in 100 nanoseconds, 10 to the fifth steps, that means a picosecond residency time. Now, I'm thinking that in our experiments, we're not optimized. We don't have a phonon laser going. But if you had a phonon laser going, you've got 7 orders of magnitude more phonons happening, then your picosecond, can turn into a much smaller number. Certainly sub femtosecond. So that could make the first step or two pretty efficient. Then the down conversion continues into lower excited state nuclei. So I'm thinking that initially the host lattice, simply numerically, since there's more of them, will participate in the early steps. And then eventually you get to the point where you're looking for states at lower energy than palladium has available. So in this case, you're looking for impurities. And if you have the right impurities, you can get excited nuclear states at tens of keV. And once you get there, the down conversion from tens of keV directly into phonons and going to ground state nuclei, I think is both possible. And I think I have, I think during this last 2 years, I think I figured out exactly how those models and that down conversion process works. So the energy would then end up vibrational, but it didn't start out. I mean, there is no reasonable way to start out and chop up a 24 MeV and slice and dice it into a large number of terahertz phonons. On the other hand, if you have fast excitation transfer processes and states around that don't decay immediately, then you can do most of your subdivision down to tens of keV, where from there direct down conversion the rest of the way is possible. If worse comes to worse, Mercury's got a 1.5 keV transition. So, but in any event, the LETS 2 laser experiment is, and Mitchell's Raman experiment are both consistent with the significant fraction of nuclear energy going into the vibrations when things work really well. In the Piantelli experiment, they get a lot of transmutations. And in that experiment, I'm thinking that the down conversion doesn't work all that great, that you're losing a significant fraction of your energy, which you'd like to down convert into destroying nickel nuclei and causing them to fizz. I think in the hot spots that Babirian was talking about, I think that's what's going on. I think in a hot spot, I think instead of multi-terahertz optical phonon mode being the carrier of this energy, I think you get an acoustical mode, a little bit lower frequency that gets the energy. And palladium can be about 5 terahertz. And in this case, the palladium nuclei themselves couple to the vibrations. And I think what happens is that it accepts, well, phonon exchange. I think multiple phonons exchange events happen among a common set of palladium nuclei. And I think it ends up spinning them up. And I think they spin up high spin states and reach, basically these high spin states can fly apart. And I think the coherent dynamics requires the flying apart to be slow, which means that it has to be arranged for the lattice to take most of the energy, the exothermic energy, which is why I think the hot spots are hot spots. They're getting the vibrational energy directly from the palladium nuclei's fuel instead of the D2 to helium 4's fuel.
Thank you.
Okay, thank you, Peter. So any other questions, any other comments for any other talks? So if not, then let me just take this opportunity to just give a little applause for all the speakers. Thank you all very much. And so we meet again tomorrow. So I close the session today. Thank you very much.
Thank you.
Goodbye. It's good night for us too right now. Maybe good morning for some, good afternoon for others. Maybe everybody should open up their, let me see.
Bye-bye.
Yeah, this is me. Bye everyone. Okay, so thank you.
Bye bye. Bye, Peter. Bye.
All right, so I'm
Glad to-
closing the.
Glad to see
So
you.
our next meeting will be at 2:30 GMT.
Yeah.
Tomorrow morning for us in India.
Yeah, so I hope all of you will be able to join again. We had a very exciting first session.
Yeah.
I hope and I also I wrote this in the Slack channel. See, one of the issues we are all facing is how do you get this whole field into the mainstream? Okay, so I hope you've all been in this for 30 years, you have probably a lot of views. So if you can share those views, how to strategize and get it to the next generation of students especially, that'll be great. So we can probably discuss that in the session 4. In session 4. I hope you all continue to show up for the next 3 sessions.
Thank you.
No, I'm the chair for session 4. I'm marketing that session. Okay, let me put it that way.
Well, tomorrow morning session, I think session 2, I think will be difficult for people from Europe and USA. And 4, we hope to see all of you again.
So thank you.
So
yeah.
we say goodbye then. Okay. Goodbye now.
Thank you.
Bye. Bye.
Bye. So shall we end the meeting? Bye, Professor Chalani. So I'm ending the meeting. Huh?